So your model is slow and you have gone looking for what to do about it. And there are about 20 things out there with names: quantization, speculative decoding, continuous batching, page retention, and every article lists all of them. And every single one of them is a real technique that really works. And most of them will do nothing at all for your server and your problem. And it isn't that they are bad. It's that most of them fix a problem that you might not happen to have. So, how do you tell which ones are yours? That is what I want to give you in the next 15 minutes. And we are going to do it as 5 questions, and you can answer all 5 of them today on the server that you already have with arithmetic. You do not have to install anything. I'm Mani Khanuja, Principal Generative AI Specialist Solutions Architect at AWS. Now, let me give you the picture we are going to use all the way through, because I think it does most of the work for us. So imagine a kitchen, and there is a very fast chef in it, and the pantry is behind a very narrow door. So now your chef can chop faster than anybody. But every dish needs ingredients carried through that door one armful at a time, right? So if you go and hire a faster chef, what changes? Nothing. And that is the most inference optimization advice right there. And we will come back to that door at the end. And hold on to this one all the way through. One H100, 8 billion parameter model, one person waiting for their answer, and nobody else on the card. How fast can that answer probably arrive? There is a hard ceiling on it, and nothing you write in your code goes above it. And we would work it out together in about 6 minutes. So the first question, and we have to do this one first because everything after is a trade. What are we actually optimizing for? Because we cannot have all of it. There are 3 things people trade between, and they are latency, throughput, and cost. So throughput is how many tokens the whole server produces in a second, and that is the one the finance team feels. And the cost is that same thing turned upside down, so dollars per million tokens. And latency is how long one person waits. And this is where I see most explanations go wrong. So bear with me for a second. Latency is not one number, it is 2. And they are set by 2 different parts of the same request, and they move independently of each other. So the first one, you hit enter and the cursor sits there, and then the first word appears. So that whole wait is one number, right? And it is called time to first token. And the second one is the gap between every word after that. So the model writes one word, then the next, and each one of those spaces is called the inter-token latency, or ITL. And if you take all of those gaps across one request and you average them, that is TPOT, time per output token. So they are not the same number, and I want you to keep them apart, because ITL is the whole spread and TPOT is one number pulled out of it. We will use TPOT later because you cannot divide by a spread. So how does that split matter so much? Because a change that improves one of them will quite often make the other one worse. So somebody watching a chat window, they will forgive you a second before the first word shows up, as long as the words after it arrive faster than they read. And a pipeline feeding another agent will forgive you nothing, because there is nobody reading and every token gates the next step. So here is your action. Before you change a single line of anything, write down which of those 2 numbers your users will actually feed. Because if you do not do that, every optimization after that is a coin flip, and you will not be able to tell whether you helped or not. So second question, and there is a fact underneath this one that everything else in this video sits on. Which half of the request is slow? Because one request has 2 halves, right? And they do not run out of the same thing. So the first half is reading your prompt. Your whole prompt arrives at once. So every word can be looked at the same time as every other word. And that makes this half a big pile of math done in parallel. So that is your chef going flat out. And people call this half prefill. The second half is writing the answer, and it is completely different shape. Your model writes one word at a time. Then it uses that word to write the next one. And then it uses that one to write the next. So it cannot run ahead, and it cannot be parallelized. And every single word is its own little trip. And here's the part that surprised me when I first sat down with it. To write one word, your model reads every one of its weights out of the memory, all of them. Not a clever subset, the whole thing. And then it does it again for the next word. So that is our narrow door. Every word in one trip through it, and it's carrying the entire pantry, right? Such big thing. So do our halves run out of the same thing? They do not. Reading the prompt runs out of math, writing the answers run out of it. And bandwidth is just how many bytes a second your memory can hand over. And almost every confusion in this whole field starts with somebody treating them as one thing and putting a single number on both. So what do you do with that right now? Go and look at whether your traffic is mostly long prompts and short answers, or short prompts and long answers, because that tells you which half of your machine you live in, and we are about to put a number on both of them. So third question, and I think this is the one that decides what you do on Monday or any weekday. Basically, what wall are you standing at? And let us go and answer that question I left you with, because we now have everything we need for it. One H100, 8 billion parameter model, and at 16-bit precision, that is 16 gigabytes of weights. One person waiting, nothing else on the card. So to write one word, the model reads all 16 bytes out of memory. And how fast can H100 bytes move? 3.35 terabytes per second. So we divide 16 gigabytes by 3.35 terabytes, and one word takes about 4.8 milliseconds. And that gives us a bit over 200 tokens a second. And that is the ceiling. Nobody beats it with better code. You can write the most beautiful kernel anybody has ever written, and you will not go above it, because those bytes still have to move. So now, watch what happens when we change one thing. Same model, same code, same everything, and we just put it behind a different memory. And A100 gives you about 125.7 tokens a second. And H100 we just did about 209. And an H200 about 300. And a B200 about 480. So what actually changed there? It was not the model, and it was not your code, and it was not the compute either. All that moved was the bandwidth. So that is what people mean when they say memory bound. And the opposite of it is compute bound, is when you genuinely are waiting on the math, and that is your pre-fill half. And it also happens when you push your batch size high enough that the chef finally becomes the problem. So those are our two walls. And here is what I would really like you to take away from it. If you're standing at the memory wall and you go off and optimize your kernels, you will spend a week and nothing will come back to you, right? Not even a small gain, nothing. So before you spend that week, it is worth about at least 10 minutes finding out which wall you are actually on. So fourth question, and this is the one you can answer tonight. How do you measure which wall without installing a thing? And before I give you the two numbers that do work, and I want to warn you about one we all reach for first. So, and I used to do it all the time. So you run NVIDIA SMI and it says GPU utilization is 100%. So your card is completely busy. And is it doing the work you paid for? That number will not tell you. It is not measuring how much of that card you are using. So go read NVIDIA's own one sentence definition, and it is counting the fraction of time that at least one kernel was running, and at least one. So an H100 has 132 of these little processors on it called as SMs. And if one of them is busy and the other 131 are sitting idle, what does that number say? 100%. So it is a fine check for whether the server is alive, right? But it is of no use at all for whether it is fast. And the two numbers that do tell us are one division each. So for your reading half, you take the operations your model actually did in a second and you divide by what the chip can do in a second, and people call that MFU, model flops utilization. And for your writing half, you take the bytes you actually moved in a second and you divide by the bytes the spec sheet says that card can move, and that is MBU, model bandwidth utilization. And notice what you needed for that second one. The size of the weights and your TPOT, the average, because we cannot divide by the distribution. And your TPOT is already sitting on a dashboard you already have. right? So no profiler, nothing installed, and nothing restarted. And one honest thing before you go and do it, and I did go looking for this myself. There is no published good number for either of them. Nobody has a table telling you that 50 is healthy or 30 is bad. So do not go chasing somebody's blog post for a target. Measure your own this week and write it down and watch it. And the day it drops 8 points, something in your deployment has changed. So figure those out. Create your baseline first. So, fifth question, and this is the one you came for. Which of those 20 techniques are yours? And now we can sort them because we know which wall we are on. So, if you are memory bound, bandwidth bound, and for the writing half at ordinary batch sizes, you very probably are. Then everything that helps you is about moving by fewer bytes per word or getting more words out of that one trip. So, quantizing the weights, that is making each number smaller so there is less to carry. Sharing attention keys and values between heads, and that goes by MQA and GQA and MLA. Speculative decoding, where a small fast model guesses several words ahead and the big one checks them all in one pass. And bigger batches, because you are paying for the trip through that door anyway, so you may as well serve more people with it. And if you are compute bound, that is your prefill, basically long prompts and very large batches. Then what helps you is doing the math better or faster. So better attention kernels, and flash attention is the famous one. Chunked prefill. And then there is tensor parallelism, where the math gets split across several cards. And there is a third group that is neither wall, and this is the one people forget. Sometimes you have simply run out of the room. So the cache of the past conversation fills the card and requests start getting evicted and then recomputed, and your throughput goes down while you are adding load. And that group is solved by page attention and continuous batching and cache management, and at the far end, splitting the two halves onto separate machines known as disaggregated serving. So there is a map, right? And every one of those has a real depth to it. And I'm not going to pretend that I have taught you any of them in these 90 seconds. Attention on its own is about like 4 episodes. Flash attention is exact, by the way, and not an approximation. And that surprises nearly everybody. And why it is true is a whole episode of its own. But you do not need that depth to make today's decision. You need to know which column you are in so you can ignore the other two. So those are the 5 questions we came for. What am I optimizing for? Which half is slow? Which wall am I at? How do I measure it? And what techniques are mine? And everything else you read about this field, it is detail attached to one of those 5. And here is what I would do tonight. And it is 3 things. And none of them takes long. First, take your teapot off the dashboard you already have. Second, work out your MBU with it. So your weights in bytes plus your cache divided by that teapot over the bandwidth on the spec sheet. And third, and this is the one that actually settles it, double your batch size and watch which number moves. So if your throughput goes up and your teapot hardly moves, you are memory bound and you still have room. And if your teapot starts stretching and you have met the other wall. And if your throughput goes down, you have run out of room and you are in that third group. Then write that answer down next to your latency numbers and treat it as your baseline. Because when somebody tells you the server got slower, you will be able to say which half of it got slower. So back to our kitchen. Your chef was never the slow part. It was the door all along. And every word your model writes goes through it carrying the whole pantry. And no amount of hiring changes the width of that door. So before you go looking for a faster chef, go and measure your door. And you know now exactly how. That was the map of this whole field in 15 minutes. So if you want the territory, I'm walking through all of it properly on this channel, an episode a day, 5 to 10 minutes each, max 15 minutes in order, and it is free. The playlist link in the description below, and I would start at the beginning. If you have been through this video up until here, do subscribe because it helps more than you would know. See you there.